Thanks very much for the introduction. So now I will present this joint work with Mohannad, Andrei, Rahul, and Earlence on trigger action platforms. So today's internet users are using a large number of services to manage their digital data or cyber-physical IoT devices. But working across different services still remains a very challenging task, as these services are built with APIs that don't understand each other. Trigger action platforms like IFTTT and Zapier is a new kind of online system that aim to solve this problem. The purpose of a trigger action platform, or TAP, is to become a centralized hub that connects to many other services. Specifically, TAPs empower automation rules by categorizing services into triggers and actions, so that the users can connect one trigger with one action to form rules, such as if I receive a new email, then ring my smart speaker. However, as great as they sound like, TAPs also raise serious privacy concerns. We will show that they are overprivileged at two different levels, allowing them to access far more data than what they need to function, thus violating the principle of data minimization in GDPR. I will then talk about minTAP, which is a system we designed to enhance privacy by leveraging language-based dependency tracking techniques. I will also talk about the privacy benefits of deploying minTAP on existing TAP providers. So here we use IFTTT, which is one of the most popular TAP providers, to illustrate the privacy concerns in real context. IFTTT has 20 million of users with connection to more than 600 services. Being such centralized hub of user data, IFTTT is not only susceptible to hacking, but its term of use explicitly states that it may provide you data directly to third parties. Services like Gmail has already removed its triggers from IFTTT due to privacy concerns, thus limiting the functionality of IFTTT. We now show how exactly TAP is overprivileged in two levels. The first one is at token level. This one has already been pointed out by prior work. Basically, say that if a user only has one simple rule that triggers when a new file is uploaded to his Google Drive, IFTTT will in turn request a very powerful token from Google that can basically do everything, including reading, sharing, or even deleting your files. The reason behind this design is to improve user experience, since this token exchange process requires user input, such as going through an authorization prompt like this one, which I'm sure many of you have encountered before. So by acquiring an all-powerful token during the first time, TAP can avoid such an annoying process if the user wants to create a new Google Drive rule in the future. The second level of overprivilege comes from the attribute level. This time, let's assume the rule gets a bit more complicated, where it only triggers on some specific condition, say that like only when the file is uploaded during work hours, and only a subset of attribute is needed. However, since Google Drive has no notion of what the user actually wants, it will keep telling the TAP about every file the users have uploaded, as well as every attribute of the file, even though if you recall the original rule, like the majority of the data is really not needed to perform the rule's action. So our solution to this problem is minTAP, which is a design of the trigger action ecosystem, where trigger service should only send data that are necessary for rule execution. In addition, it allows for computation, which is an emerging new feature provided by TAPs to express rule conditions in JavaScript. Finally, it should be backward compatible with the current system, so minTAP can be deployed readily to systems like IFTTT without requiring changes at their end. So first, let's briefly go over the current design of TAP. The users first program a rule through a TAP client, which usually takes the form of a smartphone app or a web page. Then, whenever the trigger event happens, the trigger sends the data to the TAP. The data consists of several attributes. to describe the event, which in this case, we have the name, the upload time, the path, and the content of a new file. Then the TAP will compute the rules function on the trigger data to output the action data and forward it to the action service. In minTAP, we model the TAP as a compromise party. Under this threat model, we now instruct the client to compute a minimizer that satisfies the following condition. The output of applying the original rule f on the trigger data is equivalent to first applying the minimizer and then applying f. In this way, we can think this minimizer as a preprocessor on the trigger data and has no effect on the output, which is the action data. The minimizer will be applied by the trigger service on the trigger data whenever the trigger event happens. The goal of the minimizer is to remove all the attributes in the trigger data that are not needed to execute the action. So in our toy example, attributes like path or content will be sanitized and replaced by some garbage values. Finally, on the TAP, instead of running on the trigger data, we will now run on the minimized trigger data. However, because of the guarantee that this minimizer M provides, the action data will always remain unchanged, while the TAP learns significantly less data. So, how do we generate this minimizer? First, look at the structure of an automation rule. It is composed of an if part and a then part, which is the trigger and the action of this rule. Like whenever a new file is uploaded to your cloud drive, please send a notification message, whose content includes the name of the new file. Recently, TAP providers are beginning to allow users to additionally specify this so-called filter code part in the rules. This filter code can be used for two purposes. One is to instruct the TAP when the actions should be skipped. The second is to replace some of the action values dynamically. Like in this example here, when the file name extension is JPEG, then set the file content as the attachment of the notification. In minTAP, we provide two different variants of the minimizer that have different trade-offs. Here, I will provide some high-level intuition behind each minimizer. Please refer to our paper for more details. The static minimizer is very straightforward. By applying a static analyze on the filter code and the action configuration, we can find out which trigger attributes will appear in the rule. By contrast, this dynamic minimizer takes the actual trigger data as input, in addition to the rule information. To determine a more precise set of the required attribute at our runtime, it enhances and transforms the filter code into a data dependency tracking function that returns the set of attributes accessed and the set of action values overwritten, as if the original filter code were to be run by the TAP. This dynamic minimizer is most effective when there is a skip. Now we see that the timestamp is at 4 o'clock and the condition of the skipping has been met. So no data needs to be sent to the action services. The trigger service can simply abort the process. By comparison, this dynamic minimizer exhibits high precision, especially when branching exists in filter code, but it also imposes more latency overhead due to the need for runtime execution and sandbox isolation. So the overall data flow of minTAP goes in the following order. When the user sets up the rule, the client will compute the minimizer and set it a part of the trigger attribute. In the execution phase, when the TAP tries to call the trigger API to pull the data, it will automatically pass the minimizer to the trigger service, at which place we extend the existing TAP compatibility layer in these services to execute the minimizer and to sanitize attributes. In addition, to prevent malicious tampering of the minimizer, the client will also include a signature. To account for this change, we also extend upon the existing service authorization protocol or auth to allow the trigger service to additionally recognize a legitimate user's client and accept a client public key without requiring additional user input. The second part of our study is to understand the level of overprivilege in the wild. For this, we crawled apes to collect a dataset of automation rules. We created a new strategy for crawling apes, which allows us to acquire the detailed configuration inside each rule, including the filter code and the exact rule configuration, which is both of which is crucial to our analysis and are impossible to get via previous data collection tools. We filtered out rules that are connected to public triggers like weather and news, and we end up with around 34,000 rules connecting private triggers, the triggers associated with users' private or personal accounts. The figure on the bottom right shows a CDF of the number of attributes per rule, and we can see that more than 50% of these rules have access to more than 5 attributes. By analyzing the rule conditions, we found that on average, out of these attributes, 3.6 of them are not needed for rule execution. The CDF of these attributes are shown in the orange line. If minTAP were to be deployed, all of them will be sanitized. In addition, we manually examine and categorize these unused attributes and found that the majority of them represent highly sensitive information, like users' personal information, location, or direct downloadable links. This result undoubtedly gave us a warning that the problem of overprivilege in current tabs is a serious threat to the privacy of user data, and we hope solutions like our minTAP could start to take off and help to alleviate such problems. So now I will open the floor for questions, and you may also contact me offline or check our artifact in GitHub.